Hi, this is Kevin Ega again. Welcome back to Math 250 Calculus 3, Lecture 4. So today we're going to talk about Green's theorem. Green's theorem is a really remarkable theorem, and it's section 13.4 in your book. Here it is. Green's theorem just looks like this. Okay, and just to pick it apart to figure out what in the world this is saying. Look, on the left side, you've got this line integral. It's a line integral of the type p dx plus q dy. So if you remember, that is equivalent to an integral of f dot dr. So that's what we have on the left. On the right side, we've got a double integral. This double integral is over this region D. And so here's a region D here that I've drawn here. And this integral here, I'm going to take this q, take the partial derivative of q with respect to x, partial derivative of p with respect to y, and it's going to subtract it. And that's what I'm going to integrate on the inside. Okay. And this is going to be equal to this line integral. Line integral over the curve. Okay, this thing here is, I've drawn here, is the boundary of D. Okay, I know it looks like a partial derivative sign. It's the same symbol, but it doesn't mean partial derivative here. It means boundary. So it's not related to partial derivatives, so don't think that it is. And you won't get confused because this, instead of a function, you have a region here. So that's how we know that they're talking about boundary and not partial derivative. All right, so this is this boundary of the region. Okay, it's going to be this loop. And the other thing is this is oriented counterclockwise. Okay, so it's going to go counterclockwise like this. That's what this is. Okay. Of course, if it goes the other way, clockwise, then you just put an extra minus sign and you can make it go the other way. Okay, so that's what Green's theorem is. How would you use Green's theorem? Well, there are two ways to use Green's theorem. Either you're given an integral, a line integral like this, and you'd prefer instead to calculate it like this. So you just, you're asked to find this line integral. You instead calculate this double integral, and that gives you the same answer. Or the other way around. Maybe you're asked for this double integral, and you'd prefer to find this line integral. Okay. Well, actually, one of these is a little bit easier to see how you're going to use. If you're given this line integral, okay, it's basically p and q can be anything here. So this is an arbitrary integral of f dot dr. Now it does have to be on a closed loop, okay. But if it's not a closed loop, then Green's theorem has nothing to say about that. But if it is a closed loop, then we can just use Green's theorem to instead do this. Okay. Take the partial derivative of q with respect to x, partial derivative of p with respect to y, subtract, find this double integral. And if this is easier to do, then go ahead, do this, and Green's theorem says you're going to get the same answer. Going the other way is a little bit harder to see when that would happen. The problem is, if you have a double integral, it's kind of hard to see whether the thing you have here is of the form q sub x minus p sub y. Okay. There are cases where you do use it that way, and the book gives an example of finding area this way, integrating 1, right, instead of doing this. But most of the time you're going to go from, the book is asking you, or somebody's asking you to find this line integral, you want to find this instead, and Green's theorem says those are the same. So let's look at an example like that. Let's say we have this kind of integral that we need to do. So, right, let's try it. Here's an example. Okay. Find this line integral, 3xy dx plus 4x dy. The curve here is a triangle with these vertices 0, 0, 1, 0, 1, 1, oriented counterclockwise. Of course, you should draw a picture. There it is, 0, 0, 1, 0, 1, 1. Now you know what triangle they're talking about, and it's oriented counterclockwise. Okay. If it's a loop, by the way, it doesn't matter where you start. You just go until you come back to where you started. Maybe we start here. We're going to get this, this, this. By the way, we don't need to use Green's theorem here. Okay, you already know how to do this just directly. How do we do it? I'm going to break this up into 3 pieces. This integral plus this integral plus this integral. Okay, on each of these pieces, you've parameterized this curve, parameterized this curve, parameterized this curve. You just calculate the way we always have. Just converting it into an integral on dt. Okay? And just add the results, and this will tell us what this is. But we want to use Green's theorem, so let's see if Green's theorem makes it any easier. So, of course, this is supposed to be p dx plus q dy, so I'm identifying this is my p, 3xy, this is my q, 4x. And going back to here, Green's theorem, that's p dx plus q dy. I'm going to turn it into this. So I need partial derivative of q with respect to x minus partial derivative of p with respect to y. So I'm going to take these partial derivatives and subtract. Partial derivative of p with respect to y, that's 3x. Partial derivative of q with respect to x, that's 4. I'm just going to subtract. Qx minus py is 4 minus 3x. I'm going to integrate it over this region inside here. So this is going to just become double integral of 4 minus 3x over this region here. That's what Green's theorem would say. Instead of doing this, do this. And of course, we just do the double integral. Here I'm slicing it vertically. You could slice it horizontally if you prefer. X, the first slice is at x equals 0, last slice is at x equals 1. And each slice is going to go from y equals 0 to y equals x. So you get this. That describes the integral on double integral on this triangle. And of course, you just do it, right? And just integrate with respect to y. It's 4y minus 3xy. Plug in x, you get this, right? Plug in 0, you get 0. So this is what you get for this step. And now we just do this integral. There it is. Plug in 1, plug in 0, we get this. And so this is equal to 1. So instead of breaking this up into 3 pieces and instead of breaking this up into this integral plus this integral plus this integral and parameterizing, instead we do this double integral and we get 1. All right, so that's applying Green's theorem to solving this question. Actually, a lot of times Green's theorem is going to be used in a slightly different way. Instead of actually giving a formula here, oftentimes we are interested in understanding something in physics, chemistry, engineering. Let me show you one such example. So I talked previously about an automobile engine, okay, and it's based on a kind of engine by Nicholas Otto. It's kind of confusing. This is automobile, A-U-T-O, but it's invented by O-T-T-O, Nicholas Otto. And so I said how that works. There's a piston inside a cylinder, and the cylinder, you put some gasoline air mixture in it. The piston moves back and forth, changing the volume of your cylinder. And let in the fuel air mixture. Then you close off the valve and compress it, ignite a spark, and the thing pushes out. Anyway, this is what this looks like. This is pressure, that's P. This is volume, that's V. Okay, and the work is the integral of P dV. Now, in case you were thinking that work was integral of force times distance, or force dot distance, as I've described before, actually, this is the same thing. Pressure, if you recall, is force divided by area, and volume is distance times area. So actually, PdV that's the same thing as force times distance. Okay. All right. The idea is it's going to go through the cycle. It starts off. This is the part where the valve is open, and this is basically a low pressure because it's exposed to the outside, and that's a regular 1 atmospheric pressure. And it starts at very low volume when there's nothing there. But then I pull open pull the piston down and let gas air come in. Goes up to here. It's the high volume, and then you seal it off, compress it to here, ignite it. Pressure goes up. And then at some point it starts pushing the piston down or away, and the pressure goes down, the volume increases, and then we let out the exhaust, and it comes down here goes all the way back here. Anyway, I'm not going to give you the detailed description as to why these shapes are the way they are. The point is, we need to calculate the work on this. Now, the first thing to realize is this is an integral of the type we want. Remember, P is basically my y-axis, and V is my x-axis. So this is y dx. Okay, so this is the kind of integral that we want here. Okay, this is integral of y dx, and there's nothing here. This is going to be 0. And the next thing to realize is this is going clockwise, and we want to go counterclockwise. So we need an extra minus sign to make it go the to make it go the right way here. Okay, and at least right way for Green's theorem. And then the next thing we do here, okay, is we now have to calculate this. I need to find the partial derivative of this. Okay, so what was this? This was PdV. So actually, this P is just supposed to represent any function, but as it turns out, by coincidence, it happens to be something that I've called P here, pressure. Okay, so but this is basically the Y here. So P is P. And I need to know, okay, so this is Q is 0, so that's 0 here, minus, and I'm going to take the partial derivative of this with respect to y. Y is my P, so partial derivative of P with respect to P is 1. And this is going to be integrating -1. And there we go. So first, change the orientation. So C was this curve originally, put a minus sign, I'm now going the other way, and then I'm using Green's theorem here to turn this line integral into this double integral and take the partial derivative of this with respect to P. I'm going to get -1 here. And the minus signs cancel. Right, the minus sign, by the way, comes because this minus sign here. Okay. And these minus signs cancel, and this is just the integral of 1. This is dx dy basically, or dy dx, and that's going to give me the area of this region. And so here's the thing: the work is just given by this area. That's kind of a good thing to realize here. If I want to change the maybe details of the system, the size of the piston, the kind of gas that I'm burning, then this shape will change, and you just need to know that the more area you get, that's going to give us more work. That's going to it's going to produce more work. It's going to be a stronger engine. All right, so this is an application of Green's theorem to thermodynamics. Thermodynamics has lots of integrals of this kind, and it's often interesting to see that this relates to the Green's theorem, so that you can use Green's theorem to relate it to some other feature that might be easy to understand here. All right, so I've shown you Green's theorem, I've shown you how to use Green's theorem. Now it's time to prove Green's theorem. Okay, so here we go. This is Green's theorem. I'm going to break it up into pieces, and here's how I'm going to do it. I'm going to look at this and just look at the p parts, right? P dx, negative p sub y, and ignore the q's. And I get this. Integral of p dx is equal to double integral of negative p sub y dA. I could also just look at the q parts and ignore the p's, and then that's what I get this in this line here. Okay, so I ignore this, and it's integral of q dy is equal to double integral of q sub x dA. The idea is, it's actually that not only is this true, but actually these other equations will also turn out to be true. I'm going to prove this middle equation, and I'm going to prove this bottom equation. And you notice if you add them up, you get this top equation. This is p dx plus q dy. This is qx minus py. Okay, so I'm actually going to prove this middle equation. I'm going to prove the bottom equation. The other way I'm going to break it up is, instead of dealing with an arbitrary region D, I'm going to use a rectangle. Now, you might think, well, but my region is not a rectangle. Don't worry, I'm going to get to that in a moment. Okay. The book, by the way, doesn't use a rectangle. It allows the top and bottom to be functions, a graph of a function, so it allows it to wiggle back and forth. I'm going to just use a rectangle that's easier to think about, and we can deal with other things later. All right, so let's look at this integral here. I'm going to prove this for a rectangle. This rectangle will go from x1 to x2 and from y1 to y2. And here we go. I'm going to slice it vertically here, okay? And I'm just integrating this as an iterated integral. If I slice it this way, so there's dy on the inside, you'll notice this inside here, well, that's just the fundamental theorem of calculus. I mean, the one from first semester calculus here. Okay, this is a derivative here. This is on for a given slice here on x. X is a constant, and so this is just a derivative and an integral in the same direction with respect to y. And the fundamental theorem of calculus means the derivative and integral cancel, and all you're doing is you plug in y2 and plug in y1, subtract. Notice x is still here throughout this whole thing. This inside integral, x is a constant. Okay, and now I just split this into two integrals like this. Okay. This top one is an integral where y is equal to y2. So it's y is constant, and so that means I'm going horizontally where y equals y2, and x is going from x1 to x2. So this integral here minus this integral here, and this is the same thing except in y is equal to y1. So it's this integral here. So it's this integral minus this integral. All right, so that's piece of y. Okay, well, there's a minus sign, but I'll get to that minus sign later. On this side, we need to figure out what that is. And here we go. This is integral on the boundary of D. It's going to kind of go around like this. I break this up into four integrals. This integral plus this integral plus this integral plus this integral. Okay. This bottom integral, well, you can parameterize with x. And so that's just an ordinary one variable calculus integral like this. Okay. This is the integral here. The second one, this is this vertical one, is 0. Why is that? Well, that's because x is not changing. X is a constant here, so dx is 0. And so this goes to 0. Okay. This one here is integral going this way. Well, let's make it go the other way and throw in a minus sign. So we can always make it go the other way at the expense of adding a minus sign here. And this will be the same kind of thing except as this, except it's up here instead of down here. And here, the last one is going to be 0 for the same reason this one was 0. dx is 0 because I'm not changing x. And there we go. Do we get this minus this, which is this integral down here minus this integral up here. Now, if this sounds familiar, we talked about those kinds of integrals in this previous one when we were doing the double integral. Let's put both of those slides together. This is what we did with the double integral. Okay, this is what we did with the line integral. You notice this is the same as this. This is the same as this. So basically, they're the same, except that I have to put a minus sign to change which order the subtraction goes. And so this integral here is equal to this double integral of negative p sub y dA. And there you go. That's this this thing that we're looking to prove. Okay. This one, you won't be surprised to hear, works pretty much the same way, except instead of vertical slices, we got horizontal slices, right? And so that's this inside integral is going to take this one here minus that one. And when I do this integral, these are the ones that are interesting, and the top and bottom are going to be 0 because dy is 0 on those. And if you work it out, you get this. Okay. Same argument. There's no minus sign this time. The reason is the minus sign here was because when I went from low values of y to high values of y, it went from forward integrals on x to backward integrals of x. Okay, when I'm going for this Q version, going from the left to the low values of x to high values of x, I'm going from backward integrals on y to forward integrals on y. And so that's why there's a difference in sign. Anyway, work it out yourself and you'll see that this is all true. And now we can add the left side to get this, add the right side to get this, and that proves Green's theorem. Actually, it proves Green's theorem for this rectangle, just rectangles. And that, you might think, well, now I've got to do it all over again for other shapes. Actually, no. the next part is the coolest part of this whole theorem, of this whole proof. Okay, let's say I had, for instance, two rectangles like this, and they just abut each other like this. This is D1, this is region D2, and we can do Green's theorem on D1, you can use Green's theorem on D2. Let's say we add these two equations. So add these two together, add these two together. Let's look at this side first. This double integral on D1 plus this double integral on D2, we add them together, we're going to get a double integral on this whole region together. I'm going to call that D here. D is this whole D1 together with D2. Now let's look on the left side. This is the boundary of D1, this is the boundary of D2, and if I do this, if I add these two integrals, I'm going to add these integrals like this, and these integrals like this. And you'll notice that I went up and down on this, I traversed this edge twice. Once going up and once going down. Okay, you can see these arrows here. And so remember that when I do this integral here versus this integral here, there's a minus sign because I'm going in the opposite direction. Okay, and when I add them, these integrals are going to cancel. So what you got left is this integral plus 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 this integral. This is basically traversing the boundary of the combined region D. Okay, so one thing we see is that we have, if Green's theorem is true for this and Green's theorem is true for this, then it's true for the combined region. And now we can combine rectangles in whatever shape we want. Here's a kind of complicated one. And you notice that every time you have two rectangles that share a boundary, these cancel. They're going in both directions, and so they're going to cancel. And what you're going to have is Green's theorem for this whole region here. The double integral over this whole region being the line integral on the boundary. And that's basically how we get complicated shapes like this. Now you might be a little bit worried that this is curvy and this is like using straight lines. Actually, that's not a problem. The book tries to deal with this by making these be wavy or whatever. You don't need to do that. You just need to see that this can be approximated by rectangles, and you'll see that this is true and this is true. It's important here that p dx plus q dy be the way it is, not one of these functions ds, because that wouldn't work. But this one does work. Just changing x by a little bit, changing y by a little bit, adding it all up. This as we approximate this with more and more rectangles, we're going to get this closer and closer to this, and closer and closer to this, and that will prove this Green's theorem for general regions D. There is one kind of thing that I have not shown you yet that can happen with a region, and I'm going to call this weird regions. Here's an example. It's the region between two circles. Such a thing is called an annulus. It's a Latin word for ring. And the question is there a Green's theorem for this thing? Yes, there is. To see that, let's chop this in two, like this. Okay, and this is an ordinary region that we can use Green's theorem for, D1. This is another region, D2. Okay, and we're going to put these regions together like this. And you notice that this is an edge and this is an edge that gets that goes both ways, so they're going to cancel. When I add this to this, okay, what I'm going to end up with is, well, these things are going to go away, and what you're going to get is this. Okay, and what this shows us is Green's theorem is going to say this integral on this annulus, double integral on the annulus, is this line integral here when I go around this way, plus this line integral here. You notice C1, this one's going counterclockwise. On the inside, this is going clockwise. The difference is this one is enclosing the region. This one is excluding it. So the inside here is not in the region. Another way of viewing this is as you traverse this, the region is on your left. And as you traverse this, the region is also on your left. And there we go. This is how we view the boundary of D here. It's this curve together with this curve going backward. All right, so there we go. This is Green's theorem. Where we're going to use this is in if you recall last time, the discussion about conservative vector fields. Okay, all of these three here are equivalent, and this bottom one is just hanging out here. So we know that if f is conservative, then we have this being true, and we want to know. Let's say this is true, then can we know that f is conservative? And qx, py, those are sounding familiar at this point. Those are in Green's theorem. So let's say qx is equal to py. Well, here we go. Qx minus py will be 0, and integrating 0 will give us 0. Okay, and that tells us that this integral here, the integral of f dot dr, p dx plus q dy, on this loop is 0. And in this way, we can prove this. Now, there's some details here that I have not gotten into, and we're going to have to look at these details because it's actually more subtle than what I just said. But we'll do that next time, so thank you for watching.